All right, welcome to the after work video. Second video of the day goes from 5 to 6. So this is going to be a bit of an interesting topic. In the last video, we finished up troubleshooting addressing issues on IGPs. And as we are learning about two different kinds of IGPs, we're skipping RIP. I mean, probably should be learning about that, but I kind of got enough on my plate, and hopefully I don't think RIP's that difficult anyway. But anyway, to stay on topic, since we're learning about both ISIS and OSPF, we need to troubleshoot address issues with both IP addresses and ISO addresses as well. So we did that, finished that up in the last video. So we're moving on to another topic that's going to be hopefully pretty interesting, because this is for routing loops. So I, in between videos, did gather up a number of resources that can be used to just learn about it theoretically. That might not be enough. I would like to see if I can do something in the lab, but at the same time, a routing loop is definitely a pretty dire situation. So I don't want to permanently or even temporarily damage my lab. If it's too much, it could even burn out like the hardware. It could overheat. It's not going to explode, but it could definitely damage the hardware by having a routing loop go on for too long. But let's read all about it. I'm sure there will be some sort of another tag I think I can add is network security, because a denial of service attack could be causing a routing loop. So it's really important you have those protections, or it's really important that you have your network designed so that you can't have routing loops, or so that you mitigate against the threat of them, because that can be used as a distributed denial of service network security attack. So definitely appropriate to have this video belong to a network security playlist. Okay, so we've got a lot of loops. This is for IGP loops. It's not for, it could be for IBGP, but it's definitely not for EBGP, because the topic is IGP. If we go and look at the other topics that are going to be addressed, so I would be willing to bet at this point that configuration, oh, well, that's interesting. So there is no, so there's nothing on routing loops here under BGP. So they might just not have that on the test. That would kind of surprise me a bit, but it's I think is a topic I'm going to not give much attention in this video, just because there's a lot that I would need to cover even if I didn't cover this topic. So this is all about BGP. And yes, for IGP, IBGP, it's going to be important to be worried about preventing loops, but IBGP has a built-in loop prevention mechanism where it can't propagate routes more than one hop away. So the way you can get a IBGP route from one end of your autonomous system to the other end is by redistributing that IBGP route into an IGP, such as ISIS or OSPF, or even RIP v2. RIP v2 and RIP NG, from what I understand, are really valid and widely used protocols. When I was in networking school, the teacher kind of said, we're not going to give a lot of time to RIP because, you know, why learn about RIP v1, you know, when you could be learning about things that are much more complicated and much more widely used. And yeah, that definitely applies. I would kind of, the approach I would take though is like, yes, you are kind of wasting your time, but it is kind of in some level interesting or important to learn about the basics in order to learn the advanced stuff. So the fact that that RIP version 1 is a distance vector protocol, the fact that it sends the entire routing table every 30 seconds, and you can understand, you know, why scalability is important and what kind of the issues are and what has been done to fix that. Just kind of understanding the whole, you know, why do we live in a house? It's like, well, because there's thunder, lightning, and all these things. Yes, it's going to be important if you're a carpenter to just learn how to lay the carpet, but kind of if you don't even know why people need houses at all, it can be important to learn that as well. And I would argue that it wouldn't really take that much time. So instead of just skipping over RIP v1 completely, my advice to somebody learning networking for the first time would be just give it an hour or two, learn why it's really not worth diving in and learning to a much larger extent, as other protocols are, such as the IGRP, OSPF, BGP, ISIS, and even RIP version 2, because a lot of those problems with scalability are addressed. Okay, so this one I don't think is going to be a good one to go through. Yep, let's look at this one. So globally, for the local AS BGP attribute, so this is again for EGPs, exterior gateway protocols. We'll be learning about IGPs in this section. So you know what? I think I'm just going to skip it. Now we do have related documentation on just loops, so let's check that out. Oh, but it's for EGPs instead of IGPs, exterior instead of interior. Now they don't say specifically if this is for eBGP or iBGP, but you wouldn't really have a loop in iBGP because there's a built-in protection mechanism for it. You don't really have that protection mechanism in eBGP just because of how it's used. So yeah, this is probably worth reading here. For the specified BGP address family, allow the local device's AS path in the received AS paths and specify the number of times the detection of the local device's AS in the AS path attribute is allowed. If the count exceeds the specified loop count, the system discards the route. For example, if you configure loops 1, the route is discarded if the neighbor's local AS is detected in the path more than once. This prevents routing loops and is the default behavior. If you configure loops 2, the route is discarded if the neighbor's local AS is detected more than 2 times. So, but this is for EGPs. We're learning about IGPs. Here we go. So the impact of accepting specific versus a default from your provider. The need to run iBGP on routers that do not speak eBGP is normally a function of whether the enterprise's import policy accepts only a default route or is configured to accept specific routes. So this is enterprise networking, but it is from the, oh, yep. Juno's enterprise routing. So in the latter case, you will need to run BGP on any routers that are used to interconnect your eBGP, iBGP speaking nodes to prevent routing loops. Figure 5-7 provides an example of how inconstant routing knowledge can lead to a routing loop. The inconsistency arises from forwarding state that is known to the BGP speakers only, while other routers rely on a default route. If the routers accepted only a default or the same set of specifics, this condition would not arise. So it's kind of wordy language. One thing to understand is that when they're saying inconstant routing knowledge, they're not talking about from the perspective of an admin or a network engineer not knowing enough about routing. They're talking about the devices themselves and the way their tables, routing tables populate being inconstant. So some tables would get just a default route, some would get specific routes, and it's not configured so that it is predictable exactly how they're routing, predictable and constant, exactly what that routing knowledge will look like. If you don't have that planned out so that it's constant, you can get routing loops. But I think I'll move on from this resource. It's for enterprise, and this test is on service provider. So this looks like a pretty good resource. It looks like it's just for ISIS, but I'm sure it won't be that different going to OSPF as well. So in Junos OS, release 9.5 and later, support for ISIS loop-free alternate routes enables IP fast reroute capability for ISIS. Junos OS pre-computes loop-free backup routes for all ISIS routes. These backup routes are pre-installed in the packet forwarding engine, which performs a local repair and implements the backup path when the link for a primary next hop for a particular route is no longer available. With local repair, the packet forwarding engine can correct a path failure before it receives recomputed paths from the routing engine. Local repair reduces the amount of time needed to reroute traffic to less than 50 milliseconds. In contrast, global repair can take up to 800 milliseconds to compute a new route. Local repair and global repair are thus complementary. Local repair enables traffic to continue to be rerouted using a backup path until global repair is able to calculate a new route. A loop-free path is one that does not forward traffic back through the routing device to reach a given destination. That is, a neighbor whose shortest path to the destination traverses the routing device is not used as a backup route to that destination. To determine loop-free alternate paths for ISIS routes, Junos OS runs shortest path first SPF calculations on each one-hop neighbor. You can enable support for alternate loop-free routes on any ISIS interface because it is common practice to enable LDP on an interface for which ISIS is already enabled. This feature also provides support for LDP label switched paths, LSPs. Note, if you enable support for alternate loop-free routes on an interface configured for both LDP and ISIS, you can use the traceroute command to trace the active path to the primary next hop. The level of backup coverage available through ISIS depends on the actual network topology and is typically less than 100% for all destinations on any given routing device. You can extend backup coverage to include RSVP LSPs. Junos OS provides two mechanisms for route redundancy for ISIS through alternate loop-free routes, link protection and node link protection. When you enable link protection or node link protection on an ISIS interface, Junos OS creates a single alternate path to the primary next hop for all destination routes that traverse a protected interface. Link protection offers per link traffic protection. Use link protection when you assume that only a single link might become unavailable, but that the neighboring node on the primary path would still be available through another interface. Link node protection establishes an alternate path through a different routing device altogether. Use link node protection when you assume that access to a node is lost when a link is no longer available. As a result, Junos OS calculates a backup path that avoids the primary next hop routing device. In Junos OS release 9.4 and earlier, only the RSVP protocol supports packet forwarding engine, local repair and fast reroute, as well as link protection and node protection. In Figure 1, Case 2 shows how link protection allows source router A to switch to link B when the primary next hop to link A to next hop link A to destination router C fails. However, if router B fails, link B also fails, and the protected link A is lost. If node link protection is enabled, router A is able to switch to link D on router D and bypass the failed router B altogether. As shown in case 1 with node link protection enabled, router A has a node link protection alternate path available through router D to destination router C. That means that if router B fails, router A can still reach router C because the path from router A to link D remains available as an alternate backup path. The Junos implementation of support for loop 3 alternate paths for ISIS is based on the following standards. Okay, so yeah, this looks like something that I'll probably need to set up during the exam. I do want to just pause the video for a minute because I set up new, I have a kind of a old school temperature thermostat that just came with my apartment that I attempted to program so that the temperatures would encourage me to leave my apartment at 6 to go get an exercise or something and keep me comfortable during the work time and during the after work video, and then give me a nice sleeping temperature, and then encourage me to wake up by giving me a hotter temperature. But it feels pretty cold here right now. I don't think it's meant to be this cold, so I'm just going to pause it and check that and then come right back. Okay, yeah, just living in Texas, I've been used to it being like 80, 85 in this apartment. I kind of think 82 is, or 72 is kind of like the ideal temperature for being productive and getting work done. So that's what I set it to for my work day and for the after work video. But for some reason, it just feels a bit too cold, even though it was 73. But so I might need to just save some money and bump it up to 80 because typical weather in Texas right now. is yeah, it's 93 right now, so 72, 20 degrees less. That's gonna cost me a bit in electricity bills. And if I'm uncomfortably cold too, it's a lose-lose situation. I lose money and I'm uncomfortable. So bump it up to 80, save some money, feel a little better. Might need to try that later, but for now, I think I'm just going to stay on topic. Sorry, I kind of went on a tangent. I do kind of think that really 1, 2, 3 degrees of can actually make a pretty big difference in comfort levels. Like myself, I can detect. I think if it's just like a few degrees warmer or colder than is usual. And you know, it's a little bit relevant to this channel to bring that up because if you don't have good study conditions, it's hot, it's noisy, that's going to be a problem. And this channel is about building computer literacy. In order to do that, you do have to have a environment that is possible for you to do that. So you let me know in the comments if you want me to do like I can do a complete tangent video, and I can kind of give you a plan. If you're dirt broke, you're sitting in the library right now, and you chose to use your 15-minute reservation on the computer to just watch my video. Well, I can make you a special video if you can get. Let's see here, probably 20 bucks. It might need to be like 30 or 40, but if you can get that much money, I can probably get you a plan to set up your own personal computer at home, just using a Raspberry Pi and some peripherals. And then from there, now if you don't have a oh, actually, yeah, I can have you probably use the Wi-Fi on the well, yeah. So I can come up with a plan for you. If you're dirt broke, even if you're maybe homeless and you want to try to get a probably $20 an hour tech job. I might be able to come up with a plan for you to learn Python for under 50 bucks. Because yeah, like, well, I've got a plan for you right now. Go to the library every day, reserve a computer, and work on it. But if that's not possible due to travel, due to whatever, you can't go there every day. This plan would be to try to work on that every day, which I think is the most important thing you can do to learn something is work on it every day. Okay, so sorry for that big tangent. We're meant to be learning about IGP, loops, loop-free alternates. Well, not necessarily that. We're meant to learn about configuration and troubleshooting for routing loops for IGP. So maybe that's loop-free alternates, maybe it's not, I'm not sure, but I think I will go and look at this link protection. So the next section is configuring link protection for ISIS. You can configure link protection on any interface for which ISIS is enabled. When you enable link protection, Junos OS creates one alternate path to the primary next hop for all destination routes that traverse a protected interface. Link protection assumes that only a single link becomes unavailable, but that the neighboring node would still be available through another interface. Note, you must also configure a per-packet load balancing routing policy to ensure that the routing protocol process installs all the next hops for a given route in the routing table. To enable link protection, use the link protection statement at the edit protocols ISIS interface hierarchy levels. So let's try that. So we'll open up the lab and hopefully we'll get a fresh prompt where we got to log in again because our cron job triggered. Perfect, everything's good to go. Won't have any of those same issues. So let's see that link protection. So CLI, configure private, edit, protocols, ISIS, interface, G000, set link protection. So this is protect interface from link faults only. So I'm not sure what that means. I'm not sure what link faults only means. So now I'm of course editing the logical unit. Let's see if it's any different for the physical interface. Nope. So if I edit the physical interface, you can see it takes me right to the logical unit. And that's because this is the interfaces that are applied to ISIS. So the interfaces you apply are the logical unit interfaces because those have family ISO enabled on them. Okay, so let's continue to read. Excluding an ISI, oh, well, yeah, so configuring node link protection for ISIS, you can configure node link protection for on any interface for which ISIS is enabled. Node link protection establishes an alternate path through a different routing device altogether for all destination routes that traverse a protected interface. Node link protection assumes that the entire routing device or node has failed. Therefore, Junos OS therefore calculates a backup path that avoids the primary next hop routing device. Note, you must also configure a per packet load balancing routing policy to ensure that the routing protocol process installs all the next hops for a given route in the routing table, as you must for link protection. You need to do that for node protection as well. To enable node protection, use the node link protection statement. So let's take a look at that. So this is link protection. There's also node link protection, which is protect interface from both link and node faults instead of just link faults. Configuring an ISIS interface as a backup for protected interfaces. By default, all ISIS interfaces that belong to the master instance or a specific routing instance are eligible as backup interfaces for protected interfaces. You can specify that any ISIS interface be included from functioning as a backup interface to protected interfaces. To include an ISIS interface as a backup interface, include the no eligible. So to exclude, because it's no eligible backup. You're excluding it from being an eligible backup with the statement no eligible backup at the edit protocols ISIS interface name hierarchy levels. Let's take a look at that. So no eligible backup, not eligible for backup traffic from protected interfaces. Configuring RSVP label switch paths as backup paths for ISIS, relying on the shortest path first, SPF calculation backup paths for one-hop neighbors might result in less than 100% backup coverage for a specific network topology. You can enhance coverage of ISIS and LDP label switch paths, LDPs, by configuring RSVP LSPs as backup paths. To configure a specific RSVP LSP as a backup path. Include the backup statement at the edit protocols MPLS label switch path LSP name hierarchy level. Okay, so let's not go into this yet. We've got a whole section on MPLS, so let's not sacrifice the time we've got for this to spend it on time we'll be spending later. Okay. So, I mean, that was interesting. I guess it's not really clicking to me. I don't really understand if or how that's going to be important. Here we go. So loop-free alternates. That's going to be really important to learn about. This looks like a pretty good guide. A more detailed explanation of loop-free alternates is available in the paper Understanding and Deploying Loop-Free Alternate Routes. Yeah, so let's open up that paper. Okay, and then we'll add that to the notes. Here we will only provide a brief overview. Essentially, LFA, loop-free alternate routes, or loop-free alternatives, sorry, works, or sorry, loop-free alternates, not alternatives, not routes, loop-free alternates. Essentially, loop-free alternates works by using the IGP to pre-calculate an alternate less than equal path and ensure that the path does not create any forwarding loops. This path is then configured in the forwarding table of loop-free alternate enabled routers, allowing them to rapidly switch to the loop-free path in the event of a failure. Loop-free alternates can be configured on a per router basis, and they require other routers in the network to be aware of or supporting the protocol. Loop-free alternate can be deployed in strategic locations to protect traffic and ensure sub 50 millisecond restoration in LDP-based networks. So I think the best bet I've got, so that was actually really useful. I really liked that. These guides look really nice. So this is going to be useful as well. In fact, this whole thing might be worth a read. It's pretty small. Yeah, it's pretty short. So this is definitely going to be worth a read. So this is from the enterprise routing. So we'll skip that. So I think my two key resources here are going to be this understanding and deploying loop-free alternate feature. Yeah, so defining the problem, the solution. So let's read defining the problem right now too, because that's really important. When a link or node failure occurs, router adjacent to the error detect the failure, which in turn triggers a predefined set of actions. These actions can be triggered via loss of light or an operation, administration, and maintenance OAM mechanism, such as bidirectional forwarding detection, BFD, link fault management, 802.3AH, or connectivity fault management, 802.1AG. Failure detection first occurs in the packet forwarding engine, PFE. The PFE signals the information up to the routing engine operating system. On failure detection, the event is pushed to the routing protocol process, routing daemon. At this stage, the only thing known is that there is a failed link. There is no information available as to whether the neighboring node is down or if it is just the link facing toward the neighboring link that is down.
On notification of the failure, the routing protocol process performs two tasks. Calculates a shortest path towards the destination to choose a next hop that circumvents the failed link. Most commonly, a link state protocol such as OSPF or ISIS is used as the IGP. So that's why I'm studying those two, leaving out RIP-v2. And both of these protocols use the Dijkstra algorithm to calculate a loop free topology, also known as the shortest path first SPF calculation. I've always wondered how this was pronounced. In networking school, I would pronounce it Dijkstra, which most certainly is wrong. I pronounced it Dijkstra just now because if you've played Witcher 3, as I have, and thoroughly enjoyed it, there is a character with a name spelled this way, and the character is pronounced Dijkstra in the game. That's how they say that character's name. But let's look it up just because I'm curious.
Dijkstra, Dutch. Dijkstra, Dutch. Dijkstra, Dutch.
So it sounds more like Dijkstra than Dijkstra, but really it sounds like neither. It sounds like a Dutch pronunciation that I definitely do not have a lot of practice in being an English speaker. And being unfortunately monolingual, I know I suck. But let's keep reading. I know a little bit of Spanish, but only enough to embarrass myself. And probably, yeah, that's all I really know of Spanish, enough to thoroughly embarrass myself. In addition to the SPF calculation, the neighbors need to be informed of the link failure so that they can update their routing tables with the new loop-free topology as well. The SPF calculation is a very slow process. However, with the latest routing engines, a full SPF calculation for large networks can often be completed in the range of a few milliseconds, 1 through 5 milliseconds. In reality, performing the SPF calculation is a very small part of the overall convergence time. Rather, it's the whole of the process and communication between the various elements that consumes the most time. After the routing protocol process calculates all new next hops for the given prefixes, this new next hop information is pushed down to the PFE. So this actually, they're not defining the problem, I don't see. Yeah, so far they haven't. Yeah, they're not going to. Yeah, I don't like this. It's a bit too wordy for me, and it didn't define the problem. I think this might be better. So today, many sensitive real-time applications such as voice and video require IP networks capable of recovering from temporary fault conditions so quickly that the fault and associated recovery are imperceptible to the end user and occur under the industry standard 50 milliseconds with capabilities such as MPLS frame reroutes. Traffic engineered IP networks are capable of delivering this level of restoration speed. However, in IGP-based networks, recovery traditionally requires network-wide convergence to occur first.
And this may stretch recovery times past the 50 millisecond standards. To better understand the factors that contribute to restoration times, it is helpful to consider the two steps that must occur: detecting the failure, reacting to the failure. Depending on the type of failure, node versus link, time to detect the failure can vary, but it's usually very quick. For example, 3 to 5 milliseconds when loss of light is detected on the PHY level. Reacting to failures can take much longer because it is traditionally a control plane intensive process that requires routes to be recalculated and distributed across the network. Until now, the only possible exception, as noted above, was if a standby path were calculated and installed in the forwarding table in advance using RSVP TE and frame reroutes. This would allow the router adjacent to the failure to switch to a predetermined path without involving the control plane, dramatically improving recovery times. With the introduction of the loop-free routes feature in Junos OS, Juniper is delivering automated frame reroute-like capabilities and restoration times in networks that use LVP as opposed to RSVP TE. Loop-free alternate is a software feature. All right, so I think this is going to be good to learn about, but probably not good to learn about from this guide. It's just too much information. One of the running themes of this channel is concepts, not commands. But of course, you do need to learn the appropriate concepts. Learning concepts that aren't going to help me pass the test are not the aim of what I am doing. Okay, but let's read, do the reading here, and maybe even get started on this. So, example: preventing routing loops. Routing loops can occur when routes learned from a peer are later advertised back to that peer. Normally, such routing loops are prevented by the AS path attributes. However, the AS path cannot prevent routing loops in a network configuration with the following characteristics. BGP, so this is for BGP as well. So unfortunately, I'm really having trouble finding information about IGP routing loops. So Juniper IGP routing loops. Let's not use IGP. Let's start with OSPF routing loops. Here we go. So loop-free alternate routes. Perfect. Yeah, and now let's do the same for ISIS. Okay, I'm a big fan of these user guides. Let's just go to the top level of the user guide. Yep, and now let's expand all and search for loop. Okay, so I think this is going to be good. Yep, and I already read this, but we do have an example here, and that is configuring protection. Now this is in a layer 3 VPN. So LFA, loop-free alternate, is what that means. Okay, so let's read the, it's very long. Let's just read the first part. Per prefix loop-free alternates for OSPF in certain topologies and usage scenarios when multiple destinations originate the same prefix and there is no viable LFA to the best originator, whilst a non-best prefix originator has one. In certain topologies and usage scenarios, when multiple destinations originate the same prefix and there is no viable LFA to the best originator, whilst a non-best prefix originator has one. So this is a really weird word to use. If we go to Google, search it, we can see it was really popular in the 1850s, but in 2010, I guess it's had a resurgence, but it's really not a word that is used very often. So personally, I don't really know what it means, but if it's anything, oh yeah, so it just means while. So they could have just said while, and then this sentence would have made sense for me. In certain topologies and usage scenarios, when multiple destinations originate the same prefix and there is no viable LFA to the best prefix in major, while a non-best prefix originator has one. So that makes more sense to me, but this whole sentence still does not make sense. And I have a feeling the reason it doesn't make sense is because the author who wrote it used a word whose popularity peaked in the 1850s. All right, so per prefix LFA is a technology by which the LFA to a non-best prefix originator can be used in lieu of the LFA to the best prefix originator to provide local repair. This can be used to increase the local repair coverage for the OSPF protocol also. Oh, this whole thing is really, I do not like the grammar and syntax that's being used for the language in this article. Per prefix loop-free alternates, LFA. Loop-free alternates, LFA, is a technology by which a neighbor can be used as a backup next hop to provide a local repair path for the traffic to flow temporarily in case of failures in the primary next hop, loader link. For this, the basic requirement is that the selected backup neighbor provides a loop-free path with respect to primary next hop towards a destination originating a set of interior gateway protocol IGP prefixes. The following topology explains the deployment case where per prefix LFA feature is applicable. ABR1 and ABR2 are area boundary routers. ABRs dual home to an IPv6 core network. Okay, well, shoot. Yeah, it looks pretty much the same as the ISIS one. Oh, looks like a pretty good example here. So one thing I think I would like to do, and I'm just about out of time. I've got a food delivery coming at 6, so I really can't extend this video. But I would like to, in the next video perhaps,
kind of deconstruct this and take away their topology and choose my own and kind of figure out what they're getting at here and understand it a little bit better. Yeah, we're going to need to set up RSVP, PLS, all that. I kind of said earlier I didn't want to get into that prematurely, but it's going to be one of the main things on the test. So there's no sense in learning about how to play basketball and only learn about shooting and not do any dribbling at the same time. Like, you're gonna have to. You might as well dribble the ball in between your shooting practices. So we're gonna incorporate dribbling, and by that I mean MPLS into our studies of IGP loops. One thing I would like to do before the end of this video, though, is just the classic strategy for learning about the subject matter on this exam, and that's using help apropos, because that will be available during the exam. There we go. So we've got all sorts of things. I don't know what VT means. Why is that showing up? Because I think that's virtual tunnel. Because it's loop back. So clearly we're not going to be learning about loop back. We're going to be learning about loops for IGP routing loops. So let's try this. Nope. Nope. But we do have this RFC 1583, which looks interesting. Let's take a look at that. Oh. Okay, well, it's just saying not to use OSPF version 2, but not to use an out-of-date version of OSPF version. This is the, oh. Yeah, this is the most recent version of OSP, version 2 RC 2328, and then we've got some updates to it, which are just probably extensions, further features on top of it. Yep, so authentication, multi-instance, whatever that means. Probably different from multi-areas because you're going to have multi-area. Yeah, you're going to have multiple areas just in the original one. So I don't know why they mean an extension for multiple instances. Okay, and then, yep, so interface types, transit-only networks that you can hide, I guess, security extensions, additional metrics, two-part metric. Okay, so that's not anything to take note of. So really, we're just going to be, so this is layer 2 loops, but we're talking about layer 3 loops here, routing loops, which are different from broadcast storms. It's an important thing to understand that there are 2 kinds of loops that can happen in a network that are really important to protect against. There's routing loops and there's broadcast storms. And often I have heard people get the 2 confused and use the terms either interchangeably as if they meant the same thing, or just straight out incorrectly saying that something is a routing loop when it's a broadcast storm, or saying something is a broadcast storm when it's a routing loop. So that's kind of a bad sign if somebody doesn't have that distinction properly learned, because it's, you know, it has a lot to do with the
true understanding of the terms layer 3, layer 2, which you'll hear all the time. So it's definitely not a good situation. What the heck? So there's like some bugs outside my window. I can't tell what they are, but they are the size of a small bird. Maybe they're those murder hornets or something, but those are some large bugs. Hopefully they're not the murder hornets. They probably are though. So, but let's continue looking if there's anything for routing loops. I don't see anything. Let's even go ahead and look into the help reference, even though the help topic is better, more verbose information. So we can get plenty of help for BGP loops, but that's just because you can allow groups. So globally for the local AS BGP attribute or the specified address family, allow the local devices with the wrong quotes AS number to be in the received AS paths and specify the number of times detection of the local device's AS number in the AS path attribute causes the route to be discarded or hidden. Okay, so yeah, there's two things I would like to do. In the next video, I'm going to end this video here, and I'll plan out my next video though. So I'll make goals as I did before. And hopefully my order will be here soon. So let's make a goals checklist as we did before. So we're going to use bullet points. There we go. And the first goal will be well, this might not be the first goal, but one of the goals we're going to have is this link protection example. So yeah, configuring loop 3 alternate routes for OSPF. And then another goal will be doing that for ISIS as well. There's no point in leaving out ISIS. Oh, but this is link protection. We want loop-free alternative routes. So configuring loop LFAs is what we want. All right, so let's expand this out and look for LFA. Okay, so there was an example. I think that'll hopefully be good enough. Yeah, this example here looks kind of complicated. It's over LDP, but that's not going to be a bad thing because LDP is on the exam as well. So we will need to be looking into that. And then the last goal, we're going to have more than one goal. It's going to be try to create a routing loop myself based on what I already know. So this I obviously want to try to do this goal first. So these goals aren't necessarily in order. So kind of where I'd be going this what I think would do it is redistribute ISIS to OSPF. Okay, so this will be the next video. I'll leave the tags out of it. So thanks for watching this video and stay tuned for the lunch video tomorrow. Or well, I can do a weekend video probably. So stay tuned for that, where hopefully I can finish up this topic. So thanks for watching and stay tuned for more.